Hi all, today we discuss section 2.2 subspaces. Here we have the definition of a subspace. This is analogous to the definition of subgroup in a group. We define a non-empty subset S of a vector space V as a subspace of V if S is itself a vector space under the same operations of vector addition and scalar multiplication defined on V. That is, if V is a vector space and S is a subspace of subset of V, then this S is a vector space with respect to the operations of V. That means the 10 axioms should be satisfied by this S with respect to the operations of V. Okay, then we can say that this S is the subspace. First, we have a theorem, theorem 1. That is the characterization of a subspace. That means how will you check the subset is a subspace or not. That is the idea of this theorem. This is the statement of the theorem. Let S be a non-empty subset of a vector space V with operations plus and scalar multiplication dot. S is a subspace of V if and only if the following two closure axioms or closure conditions are held. That means closure under addition and closure under scalar multiplication. If we choose any U belongs to S and V belongs to S, then their sum as elements of we can consider U plus V that should be in S. Okay, that is the closure property of the addition. Similarly, the closure property of the scalar multiplication should be satisfied by the subset S. That means U element of S and alpha is any scalar, then alpha U, that is a scalar multiple of U with alpha, that should be an element of S. So this is the theorem. So to prove this theorem, we first assume S is a subspace. That means S is a vector space as vector space in its own right, and we will prove this closure properties are hold. So that is trivial thing. When you assume this S is a subspace of a vector space V with operations plus and dot, we can say that this S is itself is a vector space with respect to the same operations plus and dot. Then we can say that the two closure properties are held because this satisfies 10 axioms. So this U comma V belongs to S, then we have U plus V belongs to S, since S is a vector space. Secondly, we choose alpha belongs to the field, or it's a alpha is a scalar, and any U belongs to S. We can say that alpha dot S is also alpha dot U is also an element of S. Since this S is a vector space, this is the two axioms for the vector space. So whenever you assume S is subspace, then you can get S is a vector space. Consequently, we have these two conditions. Conversely, we will prove by assuming S is a subset with these two conditions. S is a subset. Conversely, we will prove that S is a subset. S is a subset of V with the property that that means two closure properties are there. U plus V belongs to S for all U comma V belongs to S. Similarly, the second condition is alpha dot U is element of S for all alpha and U belongs to S. So to prove this is a subspace, first we prove this as is a vector space with respect to this operation. So to prove this is a vector space, we will prove the axioms on additivity or vector addition, that is A1. A1 is nothing but the closure property, that is U plus V belongs to S. This is trivial. This is our given condition. This is given. And the second one is associativity of the vector addition. So u plus v plus w, this is same as u plus v plus w, because this holds, because this u comma v comma w are elements of v, then this holds. And if you choose this from S, you can say that as it is elements of v, then this is trivially hold. So what is A3? A3 in A3 we can say that 0 belongs to S. In order to prove that, we choose a u belongs to S, and we consider this u, and we know that any for any u, u plus this is belongs to S. So before we prove this, we use the idea putting alpha is equal to -1 and u belongs to S. Then using the second condition, you can say that minus u, that is -1 into u, that is minus u belongs to S. Okay, using the second condition. So when u belongs to S, then we can say that by second condition minus u is also element of S. So this implies using the first condition u plus minus u belongs to S. So this implies 0 belongs to S. Okay, so this A3 is satisfied. What is F4? F4 is the existence of the additive inverse. We have already discussed that in this section. Alpha is equal to -1 and u belongs to S, then minus u. So u belongs to S implies minus u belongs to S. Now we need to prove other 5 criterion for scalar multiplication. So the first condition is this closure property of scalar multiplication, that is already given. For any alpha, alpha times u belongs to S. So that is given. Second condition is 1 times this alpha times beta times u is equal to alpha beta times u. Okay, this is also true because all these elements alpha beta are scalars, and this u belongs to S, that is subset of S, that is subset of V. So we can say that the subset of V. Then as elements of V, we can say that this holds because V is a vector space. Now we have the distributive properties of distributive axioms of the vector space. So once you consider the third axiom, that is what we call, these are called S1. This is our S1, and this is our S2. This is our S2, and that is the scalar axioms for scalar multiplication. Then what is S3? S3 is nothing but 1 times u belongs to this is always equal to u, since this u is an element of S, but that S is a subset of V. So u is an element of V, therefore in V this u satisfies this condition. So S3 is also satisfied. Now we have S4. The fourth condition is the distributive property. That we are not worried about this distributive property because these are all elements of S. Then we can easily write this as alpha times u plus alpha times v. Okay, sorry, beta times u. This is our beta times u, because this u is an element of S, that is subset of V again. So all the associativity and distributive properties comes from V, because this S is a subset of V. So this S5, what is S5? S5 is the distributive property in vectors, that is alpha times u plus V. This can be written as alpha times u plus alpha times V, because this u comma v belongs to S, that is a subset of V. Okay, so we can say that all the axioms of a vector space are satisfied by this S. So when we assume these two closure properties, we can say that the subset with these two closure properties should satisfy all the axioms of vector space, hence it is a subspace. So this proves the theorem 1. Now we have an important remark. For the remaining portion of this book, we drop the notations. This is not handy notation to write all the time this symbols is not so easy. So we leave these symbols from at this moment, because when you identify this u and v are elements of a vector space v, then once you write this u plus v, that really means that this is equal to u plus v. Okay, we are not using this notation for vector addition. Once you identify these two are vectors of v, then this denotes the vector addition. Okay, and if we have some scalars, and once you write the scalars alpha plus beta, then this alpha plus beta denotes the addition of two scalars in the corresponding field, say real numbers or complex numbers. When once you use these two elements, comes from these two elements u and v come from this v, we can say that this is a vector addition. Okay, now for a scalar multiplication, you need not worry about this symbol. If you write this alpha dot u as alpha u simply, okay, simply alpha u, so this belongs to s, or sorry, that belongs to v. It's a vector space, so we use this notation for alpha dot u, and just simply u plus v for this vector addition. So vector addition and scalar multiplication can be replaced by this symbols. Vector addition is changed to usual addition if they are using if we are using two different vectors, and this is changed by juxtaposition. That means we write alpha and u side by side to denote this alpha u. So these are the conventions we have made right now for the remaining portion of this book. Now let's see a couple of examples for subspaces. Once you write a set of four, I think we are familiar with this notation, m n r. This is set of four. This is with set of four matrices, n by n matrices aij, n by n matrices and aij, such that this a ij belongs to R. That is the real numbers. So this form a vector. This form a vector space with usual matrix addition and scalar multiplication. Now you consider a subset of M2R, say A, B, C, D, belongs to M2 by 2. This is Mn by n, and this is M2 by 2. That is a set of all 2 by 2 matrices with B equal to C equal to 0. Now consider this set. Let it be S. Okay, now you can say that this is a subspace, because this is always a subset of a vector space M2 of R, that is set of all 2 by 2 matrices over R. That's a vector space. So in order to verify this subspace, we need to verify two closure properties. First one is the vector addition. When you take A1, B is 0 and C is 0 and D1, this is an arbitrary element of the set S, and we have another element A2, 0, 0, D2. This is another element from S. So if these two are two distinct elements of this S, you can get the sum A1 0, 0, D1 plus A1 A2 0, 0, D2. Okay, this stands for the vector addition. I replaced this symbol using the convention we have just mentioned. So this is equal to A1 plus A2, and this will be 0, this will be 0, and here we have D1 plus D2. So this is always an element of S itself, because S contains the matrices with off diagonal elements, that is B and C are 0. So here we have the same form, so this is an element of S. Similarly, you can verify the second axiom or second condition for characterization of subspace, that is a closure property of the scalar multiplication. So once you take alpha multiplied with this matrix A 0, 0, D, this is the general form of an element in S, then this is equal to alpha A 0, 0, alpha D. which shows that this is also an element of S. Okay, once you take this is u and this is v, we can say that this is u plus v is also an element of S. And similarly, if you take alpha and this is u, then this represents alpha u, that is also element of S. So this S satisfies the two closure properties of the characterization of subspace. So we can say that S is a subspace. Now we have another example. S is equal to this collection. X, Y, Z belongs to R3 such that Y equal to 0. Obviously, this is a subset of R3, and we know that R3 is a vector space with respect to addition and usual addition of three tuples and the scalar multiplication. So we can verify this S is a subspace by verifying the two closure properties. So if you take since Y is 0, then the arbitrary element of the set is x1 0 z1, that is the first element, and we take another arbitrary element x2 0 z2. These are two arbitrary elements. When you add this, you can get x1 plus x2 in the first component and 0 in the second component, and the last component is z1 plus z2. So clearly this is an element of S. Okay, so we can say that this satisfies the closure property for vector addition. The second one is if you take alpha and multiply it with x0 z for an arbitrary element in S, that will give alpha x 0 into alpha is 0 and alpha z, that is also an element of S. So from this you can say that S is a subspace of R3. So to prove the easiest way to prove a subset is or a set is a vector space, to prove that subset that is a subset of another vector space and prove that it is a subspace, then you can say that that collection is a vector space. So that is the easiest way to prove a subset a set is a vector space. Now once you consider this, we know that R3 is our space. If this is our space X, Y, this is Z, then what does this subspace stands for? When you consider this as this is Z prime and this is X prime and this is Y prime. Now what is this subspace Y equal to 0? Okay, Y equal to 0 means that is a subspace XZ plane, right? So that is like this. XZ plane will be like this. Okay, this is our for this plane Y is equal to 0. So this represents represents the subspace S. This is the geometry of the subspace in R3. Now we have another subset of R3, say S equal to set XYZ such that XYZ belongs to R3 such that X equal to 3. So you can easily verify this is in this case we can if you write this is a subset, we can consider this as a subset like this. This is a subset of this is I take this is X and this is Y and this is Z. Then at X equal to 3 we can consider this as a plane. It's a plane. Okay, plane passing through. This is write it as okay. So plane passing through this point. Okay, so then we can say that this is the subspace, the subset S. We need to verify that this is a subspace. So to verify this is a subspace, we need to verify two axioms are satisfied. For that, for the first one, I take this x equal to 3 some any y or we can take it as 1 or 2. This is also an element of S, and we take another element in order to be this vector comes from this S, we need to set x equal to 3. So we take the same element or little bit change belongs to S. We can say that both are elements of S. But when you add this, you can get 6, 3, 3. Okay, but this does not belong to S because x is not equal to 3 here. X equal to 6 but not equal to 3 here. So the first property is not satisfied. So the closure property is not satisfied by this S. So this S is not a is not a subspace. Even it is not a vector space. So these are the examples and non-examples given in textbook. In the next lecture, we will discuss the next theorem, theorem for a particular subspace.